Good morning, students. Today I am going to discuss about the first law of thermodynamics for flow process. First law of thermodynamics for first law of thermodynamics for flow process. Before entering into this discussion, some of the points to be remembered. What is meant by flow process? Flow of fluids through equipments. Flow of fluids through equipments. Flow process means flow of fluids through equipments. In process industries, pumps, fans, compressors, nozzles, heat exchanger, reactors, ejector, diffuser plays an important role. Hence, flow of fluids through equipments plays an important role in process industries. Process industries. Another important point is flow of fluids under steady state condition. Under steady state condition. Flow of fluids under steady state condition is of great importance. Steady state means we have three important points. One is all the conditions are independent of time. First point, independent of time. Independent of time at all points in the equipments, apparatus, devices, whatever it means. Second point, all the rates are constant. All the rates are constant at all points along the flow path of the fluid. The second point is all the rates are constant at all points along the flow path of the fluid. Third point, there is no accumulation. There is no accumulation or depletion of mass or energy within the equipment. Third point is there is no accumulation or depletion of mass or energy within the equipment. These are all the points to be remembered. With these short memories, let us start our discussion. First law of thermodynamics for flow process. This is a open system. Open system. Open system means both mass and energy gets exchanged between system and surrounding. Both mass and energy gets exchanged between system and surrounding. Okay. Let us see this pictorial representation. This is a steady state flow process. This is a steady state flow process. Now I am going to establish the energy balance for this idealized flow system. I am going to derive the energy balance for this idealized flow system. In this system, a fluid is entering to the system at section 1 and leaving from the system at section 2. A fluid is entering into the system at section 1, leaving from the system at section 2 through heat exchanger and turbine. In heat exchanger, certain amount of energy is added to the system as heat. Certain amount of energy is added to the fluid as heat. In turbine, certain amount of energy in the fluid is utilized to perform the shaft work. Clear? This is the idealized flow pattern, flow system. For this system, I am going to derive an energy balance. The system, a fluid is entering into the system at section 1 and leaving from the system at section 2 through heat exchanger and a turbine. In heat exchanger, certain amount of energy is added to the system, is added to the fluid as heat. In turbine, certain amount of energy in the fluid is utilized to perform the shaft work. Clear? Right. According to first law of thermodynamics, the total energy with which the fluid entering into the system at section 1 plus amount of energy imparted to the fluid during its flow. Amount of energy imparted to the fluid during its flow through the system must be equal to the total energy with which the fluid leaving from the system at section 2. Okay, according to first law of thermodynamics, the energy balance is written like this: the total energy with which the fluid entering into the system at section 1 plus amount of energy imparted to the fluid must be equal to total energy with which the fluid leaving from the system at section 2. Clear? Next, conditions. Before proceed to further, what is the condition in section 1, in section 2? Okay. First, volume. Volume is represented by V. Pressure is equal to P. Height from the datum is equal to Z. Internal energy is equal to U. Velocity is equal to small u or small v. Okay, in section 1, I am using the subscript V1, P1, Z1, U1, V1. Similarly, in section 2, V2, P2, Z2, capital U2 and small v2. Okay, right. What about the contributions for total energy in section 1 and section 2? Contributions to total energy. Section 1, section 2. Okay. First point, internal energy. unit mass of fluid possesses certain amount of energy within itself by default. This energy is called as internal energy. So at section 1, internal energy is equal to mu1. Similarly, internal energy in section 2, mu2. Next, potential energy. Potential energy. This is the amount of work done against the gravity to raise the fluid from the datum level. This is the amount of work done against the gravity to raise it from certain height, is that 1. So potential energy is equal to mgz1 at section 1. Similarly, mgz2 at section 2. Next one is kinetic energy. Kinetic energy. This is due to velocity of the fluid of mv1 square for section 1. Similarly of mv2 square for section 2. Fourth one, flow energy. Flow energy or entrance work. Entrance work. Both are same. Some of the textbook they are using flow energy, some of the textbook they are using entrance work. This means a fluid entering into the section 1, a fluid entering into the system, a fluid is entering into the system is being pushed by the fluid behind in it. Okay, see, this is the fluid element, this is the fluid element. This element is being pushed by the element 1 which is behind in it by certain amount of force. Clear? Then only flow will be happen. A fluid entering into the system is being pushed by the fluid 1 which began in it by using certain amount of force. This force is propagated or multiplied by the distance through which the force acts. Clear? This force is multiplied by or propagated by the distance through which the force acts. So force into this distance is called as flow energy. Force into this distance is called as flow energy. By default, we define the work. Work is nothing but force into distance. Force into distance. Same thing. So flow energy or entrance work is nothing but fluid entering into the system is being pushed by the fluid behind in it by a certain amount of force. This force is multiplied by the distance through which the force acts. The product of force into distance is nothing but flow energy or entrance work. Clear? How can you calculate this force? This force is the product of pressure and the cross-section area of the tube. Pressure and the cross-section area of the tube. The unit for pressure is Newton per meter square and area is meter square. Area gets meter square gets cancelled. Again, the unit of force is Newton. Clear? Distance can be calculated by at a pressure P1, the fluid has definite volume V1. Clear? Volume of the fluid divided by cross-sectional area of the tube. The distance can be calculated by volume of the fluid divided by cross-sectional area of the tube. Volume divided by area. This is meter cube, this is meter square. Again, the unit for distance is meter. Here Newton, this is meter. Meter is the unit for work. So the entrance work can be calculated by the product of P1, V1 at section 1, P2, V2 at section 2. P1, V1, P2, V2. Clear? See, this is section 1, this is section 2. Total energy with which the fluid entering into the system at section 1. This is total energy with which the fluid leaving from system at section 2. This is the force at section 1 or work done on the system. This is the force at section 2 or work done by the system, because it's a forward direction, this is a reverse direction. The deficit is compensated by amount of energy imparted to the system. The next one more part is amount of energy imparted to the fluid. That can be calculated by knowing the amount of energy exchanged through heat exchanger and turbine. Okay, amount of energy imparted to the fluid is equal to amount of energy transferred to the fluid as heat. Amount of energy transferred to the fluid as heat. Here amount of energy utilized from the fluid to perform the shaft work. So the sum will be the energy imparted to the fluid. So Q minus Ws. Q minus Ws. Ws stands for shaft work. Okay. Now let us incorporate all those things in this equation. In section 1, M U1 for internal energy, for potential energy mgz1, for kinetic energy of m v1 square, flow energy p1 v1 plus energy imparted to the system, that is q minus ws, is equal to energy at section 1 m u2 for internal energy, mgz2 for potential energy plus of mv square, v2 square for kinetic energy and p2 v2 for flow energy. Okay, for a unit mass of fluid, fluid under steady state condition, for this idealized flow process, can be written like this. See this one, u2 minus u1. So this moves to that direction, u2 minus u1 plus g into z2 minus z1 plus of v2 square minus v1 square plus p2 v2 minus p1 v1 is equal to q minus ws. Clear? The net change del u is equal to del u plus g del z plus of del u square plus del pv is equal to q minus ws. This is the mathematical representation of first law of thermodynamics for flow process. Mathematical representation of first law of thermodynamics for flow process. Energy balance for open system. In most of the thermodynamic calculations, the kinetic energy, potential energy values are negligible. Hence, this equation becomes del U plus del PV is equal to Q minus Ws. This can be written like this: del H is equal to Q minus Ws. This is the final form of first law of thermodynamics for flow process. U plus PV is nothing but enthalpy. Clear? This is the energy balance equation for first law of thermodynamics for open system. This equation is widely used for solving many problems in fluid flow process. Moreover, used to estimate amount of power required to run a compressor or a turbine, something like that. Power calculation. Okay. Analogous to this equation, del U is equal to Q minus W. This is for non-flow process. That means closed system. This is open system. Both energy and mass gets exchanged. For non-flow process or closed process, only energy gets exchanged between system and surrounding. This is the equation. Okay, thank you.